Hi, I'm Harry Porter. In this video, I'm going to give a quick overview of the instruction set architecture of the Blitz-64 processor. Let's start with the registers. Each core has 16 general-purpose registers of 64 bits each. In addition, there are 16 control and status registers, and these are also 64 bits. The control and status registers are used to control the processor and to enforce the kernel protection mechanism, and they are used in context switching between user and kernel threads. There are also a number of registers called translation look-aside buffers, which are also 64 bits. The exact number of TLB registers is implementation dependent. And of course, there is a program counter. Instructions are 32 bits in length. There are only 4 instruction formats, and each instruction is encoded in one of these 4 ways. The instructions can accommodate either a 16-bit immediate value or a 20-bit immediate value. As you can see, the fields for the destination register and the operand registers are in the same place in each of the formats, which was done to streamline the hardware. In the assembly language for Blitz, the destination is consistently written on the left, that is, as the first operand. For each format, there are several assembler syntaxes. Each instruction has whichever syntax makes sense for that particular instruction. Instructions are either full-sized or compressed. We just saw full-sized instructions, which are always 32 bits. All full-sized instructions begin with 2 0 bits, while the compressed instructions use the other bit combinations. Compressed instructions may be 1, 2, or even many more bytes in length. A well-designed compressed instruction set is important to reduce the code size, which leads to less instruction fetching and increased execution speed. The compressed instruction encoding has not yet been defined, and we're planning further analysis before setting it in stone. Of course, we want to create compressed encodings for those instructions which are executed the most often. To determine which instructions are best to select for this, we need to know which code blocks are executed most frequently and what instructions the compiler is generating most often. However, in order to optimize code, the compiler must know which instructions can be compressed. So there's a bit of a chicken and egg problem here. An optimizing compiler can't choose instructions until the compression scheme has been defined. But the best compression scheme can't be determined until we know what instructions the compiler will be choosing. So finding an optimal compression scheme is non-trivial and, in general, NP-complete. In Blitz, all integer arithmetic is performed using 64-bit signed numbers. The smaller types, such as 32-bit integer, are considered legacy types. And this radical approach derives from 2 facts. First, the range of 32-bit integers is insufficient for many real-world applications, and overflow is the source of many bugs. Using 32-bit integers is just dangerous. Second, the use of unsigned integers is a highly risky, error-prone idea. The positive range of 64-bit signed integers is just so huge that there is absolutely no need to increase it by adding the idea of unsigned integers, which would involve eliminating all the negative numbers. This is anti-mathematical foolishness. The inclusion of only one type of integer in Blitz has really simplified programming, and I am convinced this is a great idea. Of course, Blitz does have instructions for sign extension and range checking, which are necessary for dealing with the smaller legacy types, but it is notable that Blitz doesn't even have a 32-bit add instruction. So Blitz is a fully 64-bit system in a way that the x86 64 and ARM architectures simply are not. Blitz has quite a few instructions, and I won't have time to describe them all in this video, but they can be grouped into the following general categories. We have the arithmetic, logic, and shifting instructions, the conditional branching instructions, several call, return, and jump instructions, the load and store instructions, instructions to manipulate the control and status registers, instructions to manipulate the TLB registers, some floating point instructions, and some other miscellaneous instructions like system call and return, debug, breakpoint, and a few others. By the way, there are no separate floating point registers in Blitz. Instead, the floating point instructions use the general purpose registers, which really simplifies things, as well as speeding up context switching. We are assuming that serious number crunching will be offloaded to some special purpose processors, so we decided to keep the floating point architecture simple. To increase the instruction set while simplifying the number of machine instructions, a number of instructions are what we call synthetic. A synthetic instruction is translated by the assembler into a simpler machine instruction. For example, the register move instruction is translated into an or immediate instruction. Sometimes the assembler may use more than one instruction for a synthetic instruction. Consider the move immediate instruction, which moves a constant value into a register. The immediate constant may be any 64-bit value. In almost all cases, it will be assembled using a single instruction. In the case where the value is an address, a single instruction using a PC relative offset will almost always suffice. But in the worst case, any address can be loaded with just 2 instructions. Likewise, call, jump, and conditional branches can almost always be translated with a single instruction, but in the worst case, 2 may be required. In Blitz, all program-generated addresses are 36 bits. Recall that immediate values in instructions are either 16 or 20 bits, so that's how we can guarantee that at most only 2 instructions will ever be needed. In fact, all calls, jumps, and conditional branches are built from just these 6 instructions, along with 5 additional instructions that help with particularly large addresses and take care of the upper bits. Here are the load and store instructions. In the first form, arbitrary addresses can be used, and in the second form, there is no limit on the size of the offset. These are synthetic instructions and are almost always assembled into a single machine code instruction, but may occasionally require more, using those previously mentioned instructions to load the upper bits. Here is the status register. There are 2 modes, one for kernel code in which privileged instructions are allowed, and one for code running in user mode, and the processor mode is controlled by a single bit in the status register. Instructions to access the control and status registers or the TLB registers are privileged, so these registers are invisible to user-level code. Another bit controls whether interrupts are disabled or not, which is necessary during trap handling. The mechanism for masking interrupts is exceedingly simple. It's controlled by a single bit, period. No interrupt levels or different categories of interrupts or selective masking schemes. And if you really can't live without these things, well, you can do it in software. There's a bit for single stepping mode to support runtime debugging, and there are some bits required by the floating point instructions. And finally, we see the address space identifier. Each virtual address space has a unique 16-bit identifier, and this is used when the hardware maps virtual addresses into physical addresses. Interrupts are asynchronous and come from the timer interrupt and I/O devices outside the core. Exceptions occur synchronously and are tied to a particular instruction. Exceptions include things like arithmetic overflows, system calls, alignment errors, virtual memory page faults, privilege violations, and some others. Exceptions cannot be masked and always invoke trap handling code immediately. Trap handling is straightforward. At the time of an interrupt or exception, the program counter, the current status word, and some information about the nature of the problem are saved into several control and status registers, which are there just for this purpose. In particular, a numerical code indicating the type of the interrupt or exception is saved in one of the control and status registers. The processor mode is then changed and a jump is made to a hardwired fixed memory location, which is the same regardless of which interrupt or exception has occurred. Thus, there's a single so-called global trap handler, which will save the processor state, essentially the general purpose registers. Then it will look at the cause code and dispatch accordingly to the appropriate handler code. Trap handling in Blitz is intended to be fast and simple, which makes sense since most time-critical computation is offloaded to device microcontrollers these days. Blitz completely avoids the complexities of a user-configurable priority scheme or multiple levels of thread priority. Blitz also has an unusual approach to virtual memory. First of all, memory mapping is always turned on regardless of the processor mode. Program-generated addresses are 36 bits, which accommodates a 64 gigabyte address range. The upper half of this range is the virtual address space. All user mode programs are restricted to addresses within this upper 32 gigabyte range, and any attempt to use addresses in the lower half will result in an exception and presumably the death of the thread. So the maximum size of any single virtual address space is 32 gigabytes. If you want larger programs, you'll just have to break your program into multiple processes. The physical memory and memory-mapped I/O devices occupy the lower 32 gigabytes. Pages in the upper half can be mapped into the lower half by the memory mapping hardware and the TLB registers, and that's what happens for user programs. Furthermore, code running in kernel mode, that is to say the operating system kernel, may also execute code and access data located in the lower 32 gigabytes directly. Since address mapping is always turned on, a kernel mode system call handler can access data in the virtual address space of the current process, as indicated by the address space identifier in the status word, without any extra effort. To map virtual addresses to physical memory, the address space is broken into pages. In Blitz, the page size is fixed at 16 kilobytes, and this is not user configurable. The decision to nail down the page size to 16 kilobytes is pretty radical. We did it because it simplifies the architecture quite a bit. For one thing, page table entries fit nicely into 64-bit registers. Second, page tables will be at most 2 levels deep, and a single-level page table will accommodate an address space of up to 32 megabytes, which should take care of the vast majority of common processes. Third, the amount of wasted memory, due to internal fragmentation within that last page, is minimal, given the size of modern memories today. But perhaps the most important thing is that the large page size reduces the pressure on the TLB registers at runtime. It also reduces the overhead when these registers have to be saved and restored, for example, when a process is paged into memory. The TLB registers can be thought of as a cache of the most recently used page table entries. But unlike a memory cache, these registers are saved and replaced in software and not in hardware whenever a page fault occurs. Here is the form of the data kept in a TLB register. The address space identifier must match the current address space identifier from the status word. The virtual page number is mapped into a physical page number, and each page table entry also has a valid bit, a couple of bits for protection, writable and executable, a copy on write bit and a dirty bit. The number of TLB registers is implementation dependent, and the TLB registers are accessed as an associative memory on every memory access where the address is within the upper 32 gigabytes. The TLB register file also keeps track of which register was most recently used. So when an eviction must occur, it will be the least recently used data that gets replaced. The instruction set contains 7 privileged instructions that allow the kernel to manipulate the TLB registers, which it needs to do whenever a page fault occurs or during context switching. So that's a quick introduction to the Blitz-64 processor architecture. At this time, we have a running assembler, linker, and compiler, as well as an instruction-level emulator and an FPGA implementation in System Verilog. Also, the project is pretty thoroughly documented at this point. What I've covered in this video is described in greater detail in the Blitz-64 Instruction Set Architecture Reference Manual. Okay, well, thanks for watching, and happy blitzing!